Okay, so in this video, we're going to talk about alkenes and a couple different classes of isomers. So first things first, an alkene is a hydrocarbon that contains at least one carbon-carbon double bond. And we're going to name these using similar rules to alkanes. We're going to take our prefix, the same group of prefixes you learned earlier this semester, and this time we're going to use the suffix -ene, E-N-E. And then you're going to number your alkene chain, and you're going to give me the position of the double bond, so the first double bonded carbon. Okay, so go ahead and pause the video and see if you can use these rules to come up with a name for this molecule on the right. Okay, so it looks like this alkene has 5 carbons, so that means we have pentene, but we have to finish this out by giving the position of the double bond. So we can number our alkene chain 2 ways. We could start at the top or we could start at the bottom. Okay, so which way gives us the lowest possible number for our double bond? So the lowest possible number is 2. So that means we want to number this way. And that gives us a name of 2-pentene. Okay, so let's talk a little bit about isomers. So an isomer is a molecule with the same molecular formula but a different chemical structure. And there's 2 types of isomers we're going to talk about today. The first one is a constitutional isomer, sometimes called a structural isomer. So a constitutional isomer or structural isomer are the same molecular formula but different atomic connections. And we can subdivide that into 3 different types. We have chain isomers, position isomers, and functional group isomers. So a chain isomer would have the same molecular formula, but we would have some kind of rearrangement of the carbon backbone. So when we're talking about chain isomers, we're talking about hydrocarbons. So a position isomer is the same functional group, same carbon-carbon chain, but the functional group is attached at a different position on the chain. And a functional group isomer is where we're using a different functional group altogether. Okay, so let's try an example of all 3 of these. So we'll start with chain. So I'm going to give you a molecule. I want you to pause this video and come up with a name for the original molecule, then draw and name a chain constitutional isomer of this molecule. Okay, so this molecule I drew was pentane, and there are 2 different chain isomers we can draw for pentane. We have 2-methylbutane, and we have 2,2-dimethylpropane. Okay, now let's do the same thing with position isomers. So I'm going to give you a molecule, and I want you to tell me what type of functional group this molecule has, and then draw a position isomer of this molecule. Don't worry about naming at this time, because we haven't learned how to name these type of molecules yet. Okay, so this molecule is an alcohol with 3 carbons. We have the hydroxy group attached to position 1. And so we could create a position isomer by moving that hydroxy group to position 2. Okay, now let's do the same thing with functional group isomers. So I'm going to give you a molecule to start with. We already know this is an alcohol. Now I want you to give me a functional group isomer of this alcohol. So remember, it's got to have the same molecular formula, but it's got to be a different functional group. Okay, so a functional group isomer of this alcohol would be an ether. Okay, so one more thing before we move on. I want you to pause the video and see if you can come up with a molecular formula for every molecule we just drew. Okay, so for our group of chain isomers up here, all 3 of these molecules have the same molecular formula because that's what makes them an isomer. And that molecular formula is C5H12. Okay, what about our pair of alcohols here that are position constitutional isomers? Well, each of these alcohols have the molecular formula C3H8O. Okay, and what about our functional group isomers, our alcohol and our ether down here? So each of these molecules should have the molecular formula C3H8O as well. Okay, so our next group of isomers we're going to talk about are stereoisomers. So stereoisomers, like all isomers, have the same molecular formula. They have the same atomic connections, but there's something different about their shape. And stereoisomers can only be interchanged by breaking bonds. So today we're going to focus on a specific type of stereoisomer called the geometric isomer. Now these are also referred to as cis-trans isomers. And these are stereoisomers that exist because of restricted bond rotation. And there are two ways that we can have restricted bond rotation: double bonds and cyclic molecules. So this is where having your molecular model kit really comes in handy. If you have it, I want you to go ahead and pause the video and I want you to make some molecules for me. I want you to make butane, I want you to make 1-butene, and I want you to make cyclobutane. And what you'll notice is that you could rotate all of the bonds on butane. They all freely rotate. But what about the other two molecules? So on 1-butene, you can rotate all of the single bonds, but you can't rotate that double bond. You have restricted bond rotation. And same thing with the cyclobutane. The rotation is restricted there as well. And so like I alluded to earlier, when I said another term for geometric isomers are cis-trans isomers, we name a pair of geometric isomers using cis-trans notation. Okay, so let's try an example. In fact, let's try the same example that we started this video off with. So we named this one earlier, but our name was incomplete. We came up with the name 2-pentene, but since we have restricted bond rotation at this double bond, we have to identify whether this molecule is cis-2-pentene or trans-2-pentene. Okay, so how do we do that? So cis means same side, and trans means opposite side. So what we're going to do is draw a line through this double bond right here. And I want you to look at the carbons attached to the double bonded carbons. Are they on the same side of this line that we drew? Or are they on opposite sides of the line? It looks like they are on opposite sides, so that means the full name of this molecule would be trans-2-pentene. Okay, so what about this one below? So this one uses something that you have not seen yet, and these are wedges and dashes. So this solid wedge right here means that this bond is coming out of the paper at you, or coming out of the screen at you. This is a trick that chemists use to show three-dimensional molecules on a two-dimensional screen. And this dash, notated by these dashed lines right here, that means the bond is going into the screen or into the paper away from you. So if we have one bond going towards you out of the plane of the screen and the other bond going away from you into your screen, that means they're on opposite sides of the molecule. So this would also be a trans molecule. Okay, so go ahead and pause the video again and see if you can tell me what the full name for this molecule is. So it looks like we have a cyclohexane parent chain, and we have methyl groups at positions 1 and 3. So the full IUPAC name for this molecule would be trans 1,3-dimethyl cyclohexane. Okay, so if you still have your model kit out, don't take your butane molecule apart just yet. We're going to talk about conformations. So conformations are not isomers. Conformations of the same molecule are the same molecule. So conformations are the different shapes that a molecule can take because of free bond rotation. So molecules in nature don't exist as a stagnant structure. They are constantly sampling different space, sampling different conformations. And all three of these molecules, even though they look a little bit different, are all conformations of butane. So which one of these is lowest energy or most stable? Well, that's going to be the one where the atoms are spread out as far apart as possible. So that means the middle conformation is going to be the most stable. So before moving on to the next video, I want you to take your butane molecule and try to rotate it to make it look like each of these three conformations here.